In this section, we'll talk about profiling. Profiling is the process of using specialized tools to measure the performance bottlenecks of your application. Despite the amazing ubiquity of these tools, many developers just don't use them. 15 years ago, I was contracted by a bank to help them solve a performance problem they were having where a huge query was taking them 7 minutes to perform. They needed sub-second performance for that specific query and were lost. They had a hard time getting profiling to work, so they wasted quite a bit of my time trying to guess the reason. I wasted a bit of time in a meeting where everyone involved raised their own theory of why this is happening. You can probably guess the end. I spent an afternoon setting up profiling, which was hard for that huge distributed system. Once that ran, I had data that showed everyone was wrong. It pointed at a specific set of calls that should have taken almost no time at all, but each was invoked thousands of times. Turns out that two guys sitting at adjoining tables had each assumed that the other guy was caching the results of a query, so they performed it each time for every entry of the table. That one change brought performance from 7 minutes to 7 seconds. Everyone has stories like these. Martin Fowler mentioned how a change in how they were getting a default constant date in a project reduced processing time from more than a day to a couple of hours. Profiling is crucial. The performance monitor is a simple tool built into the simulator that provides some insight into performance issues you might run into. The performance monitor tool focuses on rendering speed and won't help you with logical performance issues. The performance monitor tool is launched via the simulator performance monitor menu option in the simulator. This launches the following UI that can help you improve application performance. The first tab of the performance monitor includes a table of the drawn components. Each entry includes the number of times it was drawn and the slowest, fastest, and average drawing time. This is useful if a form is slow. You might be able to pinpoint it to a specific component using this tool. The log at the bottom of the screen includes debug-related information. For instance, it warns about the usage of mutable images, which might be slow in some platforms. This also displays warnings when an unlocked image is drawn, etc. The rendering tree view allows us to inspect the hierarchy painting. You can press the refresh button, which will trigger the painting of the current form. Every graphics operation is logged, and so is the stack to it. You can then inspect the hierarchy and see what was drawn by the various components. You can click the stack button to see the specific stack traces that led to that specific drawing operation. This is a remarkably powerful debugging tool, as you can literally see overdraw within this tool. For instance, if you see fill rect or similar APIs invoked in the parent, and then again and again in the children, this could indicate a problem. I highly recommend traversing the paint hierarchy in this tool and trying to explain why every graphic operation within this tree occurred. I think it would help you understand your application and Codename 1. Performance problems are usually portable. The problem is that because one platform can be faster than another, we'd often perceive of them only on the slower platform. However, with profilers, we can measure performance penalties and overhead on the desktop. We can then assume and extrapolate to perform optimizations that make sense on the device. There are plenty of performance monitoring tools for Java SE, and they all should work just fine with the Codename 1 simulator. In this case, I used the NetBeans built-in performance monitoring tool on the kitchen sink demo. The tool has two applicable modes for this case, CPU and memory. After running kitchen sink under the NetBeans performance monitoring tool, I came up with these results. This shows the threads of the application, and as we dig into them, we can see which method takes the lion's share of CPU time. The hotspots mode shows the method in which the CPU spends the most time. Both are a bit misleading, as they give a lot of time to methods that use invoke and block, another reason to be wary of this API, which is why it's always useful to isolate the area where the performance problem starts and try to measure only that section with this tool. At that point, you will be able to pinpoint the suspicious methods. It's important to read the values in the table carefully. They include both CPU time and invocations. These can expose behaviors you weren't expecting. Notice that you can click any method in the hotspots view and see the stack traces to that method. The memory mode of the profiler is a bit more limiting, as you can see. We can see the byte array take up most of all active memory, which effectively means images are responsible for the memory of the application. That's not exactly useful, as it doesn't disclose which image is responsible. We can still get a lot of useful information out of this by taking a memory snapshot and then another one after performing an operation. We can then check the change in memory and determine it acted as we expected. One of the important things we need to do when looking at a profiler is basic back of the napkin math. Do the numbers we see make sense? This is true for both memory and CPU profiler. Say your code allocates 30 images that are 130 by 130 pixels. Your memory should grow by 30 times 130 times 4, which means 2 million bytes. This will mostly show up in the byte array growth. If the memory grows by a bigger margin, then you have a problem and should try to isolate that. The same is true for method invocations. If a method takes a lot of time, then look at the elements within it. Add them up. If a method is invoked too many times, try to understand why and who is invoking that method.